Hello everyone, it's 6 o'clock. We'll wait, I guess, for 5 minutes for others to join, then we'll start today's class. If you have any queries related to the previous classes or any assignment, then you can ask in the meantime. Otherwise, we'll wait till 6:05, then we'll start today's class. It's already 6:05, so I guess we'll start today's class. I'll share you my screen. Is my presentation visible? Can anybody confirm? Okay.
Yes, ma'am.
So if you have any doubts related to last lectures of SEM or optical microscopy, do let me know. Otherwise, we'll start today's class. In the last 2 weeks, we have discussed about the SEM, how the SEM works, how the electron beam comes, or how the electrons beam is generated, and how then it comes from the vacuum column, and how it interacts with the specimen, and how the different electrons are being ejected from the specimen to get the signals which are desired for your system. So we have discussed about the SEM. So this week we'll discuss about some X-ray spectrum and as well as some diffraction techniques. So basically we discussed this in the first class itself, that the electromagnetic waves uh, travel where the electric field travels in one direction and the magnetic field travels in the perpendicular direction. So these electromagnetic radiation is considered as the wave motion, and the according to the classical theory, the electromagnetic radiation is given by E is equal to A exponential I omega t minus phi, where A is the amplitude and mu is the frequency and phi is the phase. So these are basically the electromagnetic radiation, and this formula you all know, that lambda is equal to c by mu, where c is the velocity of light and lambda is the wavelength and mu is the frequency. And according to this, energy is also given by h nu, where h is the Planck's constant, which is given by a constant value of 6.626 into 10 raised to the power minus 34 joule second. So basically these X-rays are produced when the electrons which are very which have very high velocity, which are very high acceleration, collides with your target. Is there any doubt? From my end they are moving. I guess I'll just stop presenting and share it again. Are you able to see slide number 3 with the X-ray spectrum as the heading? It's in that mode only. Okay. Is it visible now in the slide mode? And are you able to see if I am changing the slides? Right now I am changing the slides. Okay, then this is happening for the first time. I guess there is some network issue from my side. Then I'll just rejoin the meeting. Just give me a minute. Are you able to see the slides in slideshow mode now? I have reconnected it. I'll try to present it again. Are you able to see the slide mode now? Is there any suggestion? What should I do? I have tried to reconnect it again and again. Okay, I'll try. Now? Okay, thank you. Everyone else is able to see the slides now? Okay, okay then. Thank you. I'll start class. Sorry for this inconvenience. Yeah, so we were discussing about this X-ray spectrum and how the X-rays are generated. So basically the X-rays are produced when the accelerated electrons collides with their target specimen, with your target. So we have different kind of targets like copper, cobalt, molybdenum and so on. So depending upon the wavelength which you required for the analysis, basically copper K alpha is being used, but you can have different kind of target materials for the same. So basically the loss of energy of the electrons due to the impact is manifested as X-rays. So basically when you increase your voltage of your X-rays which are coming with of the electrons which are used to generate the X-rays, so depending upon that you can have different intensity of your emitting X-rays. So basically these X-ray radiations are produced in an X-ray tube only. So basically this thing you need to keep in mind, that the most of the kinetic energy of the electrons which are striking on your target, no, that are converted into heat. So there is a lot of heat generation during this process, and only 1% or less than 1% is transformed into the X-rays. So a lot of heat is generated, and only less than 1% of the energy of the electrons is transformed into the X radiations. And we all know that the energy is given by EV, or we can say it is given by half mv square, where m is the mass of electron and v is the velocity of electron. So basically from this graph you can see that as you are increasing the energy of your incoming electrons from 10 kV to 15 kV to 20 kV, initially you are getting only a continuous spectrum. I'll discuss about this continuous and characteristics radiations in the later slides. So continuous radiation basically is generated due to this loss of energy. So there is a loss of energy when the electrons are striking on your target specimen. So as a result there is a degradation in the energy of the outcoming X-rays. So as a result you get this continuous radiation spectrum. And as you increase the voltage at higher voltage, there you get these characteristic radiations. These characteristic radiations can be of different types, and these are very specific for every element. And for every element also you can have multiple characteristic radiations, like in this case they have shown this K alpha and K beta radiation, where these radiation the value of these wavelength are used for the detection of your atom. So these are very specific for different kind of atoms, and these are known as the characteristic radiations. And there is certain amount of wavelength before which the intensity is not there even at higher kV, and that wavelength is known as the lambda SWL, which is the short wavelength. This continuous X-ray spectrum, basically what happens is that continuous spectrum arises due to the deceleration of the electrons when your electrons are hitting the specimen, are hitting the target. So when your electrons are coming to the target, there can be the incoming radiation, this blue one, can go by a certain amount of deviation, and it can generate some energy, which is this shown by this yellow arrow, which is known as the X-rays, or the electron beam which is coming inside with shown by this blue line can go more deviated when it come close to the atom. So then it will have a different amount of energy will be generated in the form of X-ray. Or if the incoming electron beam is very close to the atom, then it will have different energy of your X-ray will be emitted. So this all contributes to the continuum spectrum of the X-ray, which is shown by from this region to this region. This is a continuous spectrum. There is no characteristic wavelength radiation is generated in this case. So this type of radiation is known as this Bremsstrahlung radiations, which in German is known for the braking radiation. So these are also known as the continuous radiation, polychromatic radiation, or white radiation. White radiation because white radiation is where all the wavelengths are being accumulated, so that is known as white radiation. And here also we are getting different wavelengths, so we can call it as a white radiation. Some electrons loses all the energy in the single collision with the target atom. Like here the loss of energy will be much higher in this case as compared to this first one. So there are some properties of this continuous spectrum, that is that these continuous spectrums have a very smooth curve of their intensity versus wavelength, and the intensity is 0 up to a certain wavelength, which I discussed with you previously, that this point that is known as the short wavelength limit, which is given by lambda SWL. and the electrons transfer all their energy into the photon energy itself at that point. And so that your EV will be equal to h mu, and your, as a result, your lambda SWL, that is short wavelength limit, will be given by c by mu, and your, and then after that you can have hc by e mu ev, and then if you put the constants value in this equation, you will get a equation of short wavelength limit as 12.398 into 10 raised to power 3 divided by volts, where lambda will be in angstroms and v will be in volts. This formula you need to remember for this short wavelength limit. We have just put the values of these constants into this equation, and then we came to this formula for short wavelength limit. So this total energy, the X-ray energy which is emitted per second, also depends upon the atomic number of the target material. So if you want to have, if you are having some lower atomic number target material like copper, and if you are having a higher atomic number target material like molybdenum, then you will have different intensities and different energies will be, X-ray energy will be generated from each target material. So the total X-ray intensity I continuous will be given by A into I Z V raised to power m, where A is nothing but the proportionality constant, I is basically the tube current, and Z is your atomic number, and V is your voltage, and m is just a constant which is taken as 2. So basically the intensity of your X-ray generation is directly proportional to your atomic number. So as the atomic number of your target material will increase, your intensity will also increase. So depending upon the your, basically depending upon which in how how much intensity you require for your analysis, you can have different type of target materials. But generally in most of the cases, copper is used as a target material for X-ray analysis. And then we later on at higher kV we have these characteristic radiations which are denoted as K alpha and K beta. So this was discovered by W.H. Bragg, and it was systematized by H.G. Moseley. So what does happen in this? Basically, if you have an atom and when your incident electron falls on your atom and the inner shell electron is being ejected from your atom, then the inner, you have a hole in your K shell. Then as a result, if your electron from L shell jumps to the K shell to fill this vacancy, then there is some radiation which is being emitted out. So now when your incoming radiation comes and takes the electron out from your K shell, then you have a hole in your K shell and electrons are present everywhere else. Now the electron from this L shell will jump to this K shell to fill the vacancy in the K shell, and as a result it will generate radiations which will be known as the K alpha radiation. And if the electron would have jumped from the other shell, then it would have known as the K beta radiation. So depending upon the shell like K, L, M, N from which the electron is being jumping, you can have different kind of radiations. If the electron from M shell must have jumped to this K shell, and then the radiation which have come out from this jumping of electron to fill that vacancy in the K shell, then this would have been K beta. So depending upon the shell from which it is being jumping, you can have different kind of radiations. Like in this graph which we are seeing from the first slide itself, you can have K alpha as well as the K beta. So if you are having if you want to analyze a compound which is having two different atoms, and those different atoms can have similar kind of similar energy of your K alpha radiation, then you need to have Like for one you can analyze k alpha, and for the other you can analyze k beta, like that. This is most generally used not in x-ray but in EDS spectroscopy, when you have the some overlapping of two different atoms which are having the overlapping of your k alpha or k beta energy levels. Then you can manually choose two values, like for one atom you can choose k alpha and for another atom you can choose k beta. So like that you can differentiate the two atoms and then you can get your data easily. So basically, these characteristic peaks is created when a hole in the inner shell is created by a collision event. Is someone is in the lobby? Just a second. So when the incoming electrons is generating a hole in the inner shell, and then the hole is filled by the electron from the higher energy shell, then that will generate your characteristic peak. So let a K shell electron be knocked out as we told in the previous slide, and the vacancy can be filled by an electron from the L shell, that will be known as the K alpha radiation. Or if this vacancy in the K shell is filled by the M shell, that is the next to the L shell, that will be known as the K beta radiation. So this is basically just a representation, like if your the maximum energy will be of K alpha, and then okay, you can have your vacancy can be filled from different shells, depending upon the shell which is filling that vacancy, you can have different radiations like K alpha and K beta. And if your the incoming electron ejected the electron from the L state, then you can have L alpha radiation if the electron from the M shell is jumping to this L shell. I hope this is understood to everyone. If there is any doubt, please let me know. The incoming electron can eject the electron from K shell, but if the incoming electron is ejecting the electron from the L shell and that vacancy is filled by the M shell electron, then that will generate the L alpha radiation. And if the incoming electron is ejecting electron from M state and the N level electron is filling the vacancy in the M level, then that will generate this M alpha radiation. So depending upon the shell from which the electron is being emitted, and depending upon the shell from which the vacancy is being filled, you can have different kind of radiations. Basically, usually only the K lines are used for the X-ray diffractions, but you can have different like K alpha 1, K alpha 2 and K beta 1, which are very strong radiations. Alpha 1 and alpha 2 are not always resolved. Sometimes you can have the K alpha doublet. Like in this case, if you zoom this one, this K alpha radiation, then you can see that you have two doublet of K alpha radiations which are being represented as K alpha 1 and K alpha 2. Commonly, chromium, iron, cobalt, copper, molybdenum are being used for the target element for the X-ray generation. And basically, in the X-ray diffraction, we generally use this copper K alpha radiation, which is given by which have a wavelength of 1.54. Armstrong. There is one Mosley law which states that as the wavelength of any particular line will decrease, the atomic number will increase. So basically it is given by under root of mu, which is given by C into Z minus sigma, where there is a linear relationship between the square root of your line frequency mu and your atomic number. So as your atomic number will increase, your frequency will, under root will increase. And these are some basic things for X-ray absorption. So when the X-ray encounter from any form of matter, they are partly transmitted and partly absorbed. There is nothing particularly there is nothing which will completely transmit or which will completely absorb. Everything in the nature have this nature of partly transmitting and partly absorb, but depending upon how much they are transmitting and how much they are absorbing, they are considered in different categories. So it was found experimentally that intensity will be directly proportional to your x, which is known as the distance. And if you will, and there is one differential form also. When you differentiate it, you will get di by I is equal to mu into dx, where mu is your linear absorption coefficient, and after integrating this equation you will get Ix is equal to I naught into e raised to power minus mu x, where I naught will be your incident beam intensity and Ix is basically your transmitted beam intensity, and mu is your linear absorption coefficient and x is your distance. Then I'll discuss about this diffraction. Basically we have discussed about this diffraction in the previous classes most of the times. So basically there are different approaches to understand and visualize these diffractions. So first is this Loewe conditions. Basically we all know about this Bragg conditions, where we say that lambda n lambda is equal to 2d sine theta is used for the, if you are satisfying the planes corresponding to your wavelength or not. But initially the conditions were given by this Loewe, and he got this Nobel Prize in Physics in 1914. So basically Bragg extended these Loewe conditions itself into a much more convenient form from which you can understand and you can apply directly to your systems, which is known by all of you, which is given by n lambda. I guess I'll have that in some next slides. This you all must have known, n lambda is equal to two d sine theta. So this is basically the Bragg formula which we all know, where d is your d spacing between different planes, and lambda is your wavelength, and theta is your angle between the incident beam and the normal. So these are derived first. So firstly these Loewe conditions came into picture. After that only the Bragg used these conditions and applied certain other techniques to have this very simpler formula which can apply to know the despacing of the planes. So basically these Loewe conditions are what says that when your incident beam, this AB is your incident beam, and when it is scattered by this atom B, then someone is in the lobby, I guess. So basically your incident waves are these ones and this one, and the perpendicular to this, which is shown by this green dots, will be your incident plane wave. And when you have your atoms at point B and point C, then you will have your incident beam will be scattered from these atoms, and you will have your scattered plane wave given by this BD line. So this green line dotted line represents your scattered plane wave. And according to this, you have this Loewe conditions where you have A into cos theta 1 minus cos theta 2 is equal to h lambda. Similarly, B cos theta 3 minus cos theta 4 will be k lambda, and C cos theta 5 minus cos theta 6 will be L lambda. So these are basically three Loewe conditions which are used, which are when satisfied will say that your diffraction is taking place. So this Bragg law basically uses that Loewe conditions only, but in much simpler way. So basically this black line represents your planes in your atom with the spacing d between them, and these are your incident waves which are being scattered by your planes of your atom. And when these are scattered at a similar angle similar to the incident plane wave, and you all must have known that your incident plane wave and your scattered plane wave and your must lie and your normal all should lie in the same plane. These are some basic laws. So the incident plane wave is forming an angle of theta with your atomic plane, and then if you see, just let me select the pen. If you see this first ray, it is coming from here, then it is being scattered by this plane, then it is scattering back. And your wave 2 is also doing the same thing, but with the other plane which is at a distance of d from the initial plane. So this wave is traveling certain extra path which is AB plus BC. This extra path is traveled by this second wave which is wave 2. And if we will, and we know and construct, so there can be constructive if this second wave is going and traveling an extra distance of AB plus BC, and this AB and BC are equal only, so we can say that the second wave is traveling an extra distance of 2AB. And if we will evaluate it and all, then we can get this Bragg's equation which is n lambda is equal to 2d sine theta. There can be, if wave 1 and 2 can have constructive interference or destructive interference. It will have constructive interference only when the path difference between the two waves, that is the wave 1 and wave 2, is an integral multiple of lambda. That is, if and only if the path difference between wave 1 and wave 2 will be n lambda, then only they will have a constructive interference. Otherwise they will undergo some destructive interference and you won't get the intense lines in your diffraction. We can also use this alternate vector approach, which will be very useful for describing the diffraction in the TM. So basically, if these are your atoms, these blue lines are your atoms, this is 1D plane, this is another plane, and your incident beam is coming in this direction, and then it is being diffracted, scattered in this direction. Then you can see that your incident beam, which is this K1, and your diffracted beam, it is KD. So if you just make a triangle out of this, so this is your K1, you just need to rearrange it, and this will be your diffracted line KD. Then you have generated this vector which is known as vector K. So basically the angle between K1 and KD is 2 theta. It is not theta, just remember this, because theta is basically this angle is also theta, and if you just displace this KD over here, then the angle between this KD and your incident radiation, this will be 2 theta, and related to that only you can have you this you can see this third one, where the two beams like this R1 beam and this R2 beam are scattered by these two atoms point C and this point B to generate the scattered radiation as R1 and R2. Then you can see that your scattered radiation R1 will have traveled a much higher distance as compared to your scattered radiation R2, and this also the high more distance will be given by this plus this. So this will be AC plus CD. So this is the extra distance which is traveled by your radiation R1 after scattering as compared to your radiation R2. And if the part difference between this is n lambda, that is the integral multiple of your incident wavelength, only then they will undergo the constructive interference, otherwise they will go destructive interference. Using this only, you can see this incident one is known as the Ki vector, and your diffracted will is represented as Kd, and the half of this K vector is known as the K by 2. So using this vector only, we can say that K will be equal to Kd minus Ki. Vector K, this one, will be equal to Kd minus Ki. And Kd is basically your 1 by lambda. And if you see the sine theta of this C1, if you consider this triangle, if you apply this sine theta, it will be K by 2 divided by the magnitude Ki. According to this, you will get K is equal to 2 sine theta by lambda. So that K is equal, so then you get this K is equal to 2 sine theta by lambda. Then if you So if the path difference of the two radiations, that is the R1 and R2, is given by your n lambda, where n is an integer, then you have your Bragg law as n lambda is equal to 2d sine theta b. And if you rearrange this, then you will get 2 sine theta b as lambda by d. And according to this, you have 2 sine theta is equal to lambda k. So using these two equations, you can have 2 sine theta b is equal to lambda k. So that if you compare these two equations, then you will get your magnitude of k is equal to 1 by d. So this is basically the reciprocal of your d spacing, and your reciprocal of your d spacing is given by a vector g, which we will discuss in the next slide. So basically, if you are comparing the Bragg's equation with the vector addition of this triangle, where your Ki is your incident radiation and Kd is your diffracted radiation, which have a 2 theta angle between the two, then you can get that Kb is equal to 1 by d, where 1 by d is given by the vector g. So Kb is given as g. This g I will discuss in the later slides. What is this g vector? So till now I discussed if the atoms, is there any doubt? So if the incident radiation is being scattered from one single plane only, with two different atoms at same plane only, then what will happen? So basically till now I discussed when the scattering is taking place from two different planes having a d spacing of d between them. So if two beams are scattered from two points, like in this case point E and point F, which lie in the same plane only, this P1, then you can see that your R1 radiation comes and scatter from point E and goes as EJ, and your R2 beam will come and strike at atom F and it will go as FR2. So now you can see that these two radiations are traveling the similar distance only. There is no distance difference between these two radiations R1 and R2 if they are being scattered from different atoms from of the single plane. But if the atoms are present in two different planes, then only there will be the path difference. So basically these blue lines are basically the set of your planes with the spacing d between them. So if you have your incident beam, it will get scattered from the plane and it will form a, this I'll need to have a pen. So if this is your incident beam and it falls on this plane, then certain amount of it will get diffracted, and if it goes undeviated, it will follow this direct beam path like this one. So the difference between this point O and point G is known as basically your G vector, which we initially told as 1 by D. So basically your incident beam angle, sorry, so when your incident beam is falling on your plane, then it is diffracted, and the distance between the direct beam and the diffracted beam is known as this G, which is given by your 1 by D, which we discussed in the previous slide, where G was a vector which was given by, which magnitude was given by 1 by D. And there is also some dynamical diffraction, where the beam which has been strongly back diffracted once is necessarily in the perfect Bragg orientation to be diffracted back in the direct beam by the same set of planes. What does it mean? That when your beam, which is like, for example, take this beam 1, which I am showing this with the red point. So this is being diffracted from your plane P1, making an angle theta with your incident beam. Then it is being diffracted once, then after striking to the plane P2, it will be diffracted back to have a direct beam again, this one. Like initially this was incident beam 1 was coming in this direction and it was being diffracted by this plane B1, and it was completely Bragg diffracted. So then this was this diffracted beam, this one. So this diffracted beam when hit the another plane P2, then it get reflected back and it follows the similar kind of path which was followed by this incident beam, initial one, this one. So now this diffracted beam is just parallel to your incident beam. So this is known as your dynamical diffraction. So basically your incident beam is getting diffracted twice, once with the plane P1 and once with the plane P2, and then it will have a parallel path with the your initial incident beam, that is this one beam. So basically in TM we will deal in the reciprocal space, and most of you have taken your crystallography course, where last time I discussed about with you about your evolved sphere and reciprocal lattice. So this reciprocal lattice is basically used for your diffraction patterns and all in your TEM. So basically in real space you have a vector wave plane vector which is given by r, where r is given by n1a plus n2b plus n3c, where whereas in reciprocal lattice vector you will have this vector r star, where r star will be given as m1a star plus m2b star plus m3c star, and your reciprocal vector are basically, so the in the reciprocal lattice the set of planes HKL atomic planes are represented by the single point located at a distance 1 by d HKL from the lattice origin. So basically your reciprocal lattice vector is perpendicular to your real lattice vector. So as a result your a star are perpendicular, so the dot product of a star will be 1, dot product of b star will be 1, and dot product of c star will be 1, and the dot product of a with b star or a with c star will be 0. So all these dot products will be 0, except that the dot product of a star with a will be 1, b star with b will be 1, and your volume for the reciprocal lattice will be given by b cross c divided by a star. So basically your g vector was, which I told you in the previous slides, is given by this k, where it g is given by, in reciprocal space, is given by h a star plus k b star plus l c star, where HKL are all now integers together define the HKL plane. So basically your O is the origin and you have a plane ABC, then your ON, then your OA line will represent H by A, OB line will represent B by K, and OC line will represent C by L. So as a result, if you will have, and your vector ON is perpendicular to your ABC plane, which gives you the D spacing DHKL. So as a result, if you apply this condition where B by K minus A by H into dot product of HA star plus KB star plus LC star is 0, then you will get this equation, and after solving this equation you will get that DHKL will be the reciprocal of 1 by G vector. And this we discussed that the K is equal to G, and your 1 by d HKL is given by 2 sin theta by lambda. So basically you can say that the magnitude of your incident radiation is basically the reciprocal of your wavelength, that is the reciprocal of lambda. Just keep this thing in mind, that is the value of magnitude of K is inversely proportional to your wavelength. So if we have these diffracted spots and you have your incident beam shown by this blue line, then you have this incident radiation, then you will have the evolved sphere which you all know. Then as a result, if your incident beam, let me select the pencil and explain you. If your incident beam is coming in this direction, then point O will be your origin, and the wavelength of your incident radiation will decide the radius of your evolved sphere. So radius of your evolved sphere will be given by 1 by lambda, and you know the energy of incident electron beam. So if your incident electron beam is energy, then you know radius of your evolved sphere. So then you can select a point at the center. Then you can have your evolved sphere, and the there is one thing which you need to keep in mind, that this evolved sphere can be, keeping this origin point O as a fixed point, you can have this evolved sphere in all directions. Like in all 2D, you can have a 2D rotation of this evolved sphere. So this complete area will be covered if you have this r by lambda as your incident radiation, and as a result only those points will be undergo Bragg diffraction condition, which will touch the evolved sphere. So as you can see, if this is your origin, let me clear the slide. So if this is your origin point should be your diffracted point, but your point C can be anywhere. You can rotate this evolved sphere keeping this point O constant, and you can have the limit of your diffraction in this 2 dimension, where you can rotate your evolved sphere making this point O constant. So your uh, points will only be diffracting which are touching your evolved sphere. So if this is your point O is the origin, and you can see that this point is touching your evolved sphere, so this point will be completely Bragg diffracted, and after that this point will be your undergo Bragg diffraction condition. This point will undergo Bragg diffraction condition. This point will undergo Bragg diffraction condition. And if you want other points to undergo Bragg diffraction condition, then you need to rotate your evolved sphere. For that you need to change the incident beam angle. Either you can change the orientation of your specimen, or you can change the orientation of your incident beam, so that your other spots should also diffract and should follow the Bragg condition. Only those points which are touching their evolved sphere are following the Bragg diffraction conditions. Rest all are not following that. And for that you need to orient your specimen or your incident beam in a certain way. So these are basically these points only which we discussed, that the evolved sphere passes through point O, with the center of the sphere depends upon the Ki, and Ki basically depends upon your lambda, which is 1 by lambda. It not to be a reciprocal lattice. So the center point C should need not to be a reciprocal lattice point, but the origin point O should be a reciprocal lattice point. The vector kd can be on any point on the sphere. If kd intersects the reciprocal lattice point, that means your Bragg condition is being satisfied. If your evolved sphere is having point O on itself, then only it will follow the Bragg law, otherwise it won't follow. So the radius of sphere is we discussed is given by 1 by lambda. So basically this is just the comparison of different radiations, where you have X-rays, visible rays, electron rays. So for the visible radiations, you have your evolved sphere, which is very small. I guess someone is in the lobby. Just a second. So basically in the end I am just comparing different wavelengths. So as we know that the wavelength of electrons are much lower as compared to the wavelength of the visible light. For the visible light, so the energy is lower, so the wavelength will be higher, and if the wavelength is higher, then the radius is given by 1 by lambda, then the radius of evolved sphere will be very small. So as a result you have very small evolved sphere which is given by this green circle. So in the visible light you cannot have diffraction, because your evolved sphere will, if like which I told you in this, that your point O should be your diffracted spot only, or we can say should be your reciprocal lattice point only. So if your point O is satisfying the reciprocal lattice point, then there can't be any other point which is being diffracted. And if we consider these X radiations which have a slightly higher evolved sphere as compared to the visible light, so this can touch the other points in the reciprocal lattice, but only one or two points at a single point at a single time. But these electron radiations have a much higher energy, as a result have a very high or very big evolved sphere, very high value of your 1 by lambda. So as a result, you at a single time you can have, if your origin is point this one, then you can have different spots which are different diffracted spots which are present on your evolved sphere of your electron beam. Then only these points will satisfy your Bragg condition, and only those points will be undergo constructive interference and back diffraction. So this is all for today's lecture. Then we'll discuss about the assignments. If you have any doubt in the theory, please let me know. Otherwise we'll start the questions. Any doubts? If no, then we'll start the quiz and assignments of this week. All of you, please try to answer the questions. If you have understood the theory part and you have understood the SEM part of the previous classes, then these questions will be very easy to attempt. So the first question says that choose the combination of statements which are true. The first statement is X-rays are produced by knocking out the inner shell electron from the target material using highly accelerated electron produced with high voltage. This statement is completely correct. We have discussed this in the today's lecture. And the second statement says that the X-rays generated from the target has continuous wavelength and also characteristic wavelength. This statement is also very true. The third statement says that heterochromic radiations, which is basically your continuous radiations, are used for X-ray diffraction analysis of crystal structure. These can't be used for the X-ray diffraction analysis because these are very continuous. For that you need to have your characteristic radiations like K alpha or K beta, which we discussed. So this statement is very incorrect. The statement 4 says that continuous wavelength of X-rays is produced due to the deceleration of electron hitting the target. Yes, this is completely true. The continuous wavelength is the result of the deceleration of the electrons which are hitting the target. So as a result, the correct answer will be option 1, statement 1, 2 and 4. So I guess option C will be the correct answer for this question. Is this clear to all? These are basically 4 points which we discussed in today's class, that how the X-rays are being generated. Now next question, please, I will request all of you to please try this second question, which says that an X-ray was produced at a condition of 45 kilovolt and 300 milliampere current with the copper target. If the intensity of your incident X-ray has to be increased, your intensity has to be increased to obtain a better intensity of the peaks in the diffraction pattern. Which among the following conditions would you suggest? So we discussed about this intensity, that how the intensity can be increased. We also discussed one formula where we discussed that your intensity of your incident beam will be directly proportional to your Z. So according to that, can anybody suggest what should be the correct option? Anyone, any guesses? Shailendra is saying option D. Option D is what? 45 kV, 30 milliampere germanium target. Okay. Anyone else? So using this formula, we stated that the intensity of your X-rays can be enhanced by changing your Z or by changing your V, which is the voltage. So according to this formula, you can also change voltage also. So according to me, the correct option should be option C, which says that you can have 50 kV electron beam with 30 milliampere current, and you can have a molybdenum target. The third question says choose the correct statements about the characteristic wavelength of X-rays. This you all should tell. Option 1 says on increasing voltage, wavelength of characteristic X-ray will change. This statement is correct. Yes, it's completely correct. Option B says K alpha characteristic wavelength is lower than the K beta. This statement is also correct because K alpha is generated when your electron is coming from M shell to K shell, L shell to K shell, and your beta is generated when your electron is transmitted from your M shell to K shell. So as a result, your K alpha characteristic wavelength will be lower as compared to your K beta one. And the statement 3 says that there is a critical excitation voltage to produce the characteristic X-rays. Yes, because we saw that when you are using the lower excitation voltage, you were getting only the continuous spectrum. There was not any excitation spectrum, as we have shown in the graphs multiple times, where at higher voltage only you were able to see the characteristic wavelength. So this statement is also correct. According to this, option D, that is all of the above statements are correct, which says that as we increase the voltage, the wavelength will be changed. The K alpha radiation will have a lower wavelength as compared to K beta, and there is the critical excitation voltage which is used to produce your characteristic X-rays. So all the statements are correct. So option D is the correct answer for this question. The next question says that you are asked by a company to develop a material which will be used as a shield for protecting workers from X-ray radiations. Among this, which would you choose? So basically, lead is the material which absorbs all the X-ray radiation and doesn't allow the radiations to pass through them. So according to the property of your lead should be used as your protective shield from your X radiations. So according to this, lead will be the correct answer. This question I guess you all can try and let me know the answer of this question, which says that a cubic crystal lattice which is having a d spacing of 1.327 angstroms for the HKL plane of 222, what is the lattice parameter of the unit crystal? For the cubic system, you all know that your d HKL is equal to your A, which is your lattice parameter of cubic unit cell. For cubic unit cell, A, B, C all are same. So you can just directly write A divided by under root of H square plus K square plus L square. So using this formula, can anybody suggest me the answer of this question? Your HKL is given as 222. Your D spacing is given as 1.327 angstrom. You just need to calculate your value of A in angstrom. Can anybody calculate and tell me for your cubic system? This formula is valid only for cubic system. Do you have calculators with you? Can you please calculate this value? Anyone? No one is interested? This is a very simple question, I guess. Gautam says, Shailendra says, and Balakrishnan says option A. Okay. Option A, that is 4.596 angstroms. Is this what all are getting? Let me calculate it. Your A will be 1.327 into under root of 2 square is 4. 2 square plus 2 square, 2 square will be under root of 12. So you just need to calculate this value. So under root of 12 is 3.464 into 1.327. It gives a value around 4.59. Okay. So then this practice is over. Now we'll go to the quiz of this week 7, which says that calculate the short wavelength limit of X-ray beam operating at a voltage of 25,000 volts. For this short wavelength limit also we had a formula which we discussed in the lectures. which is the short wavelength limit will be given by 12.398 into 10 raised to power 3 divided by V. So using this formula, you can anybody calculate and tell me what will be the answer of this question number 1, where you just need to calculate the short wavelength limit at a voltage of 25,000 volts. Shell in this is option B. Option B is 0.5 nanometer. Yes, he is completely correct. Anybody else have tried? Okay. Yes. So correct answer for this question is option B, which is 0.5. Which of the following statements is or are correct? Statement 1 says that the threshold wavelength limit below which no emission occurs with increase in applied voltage. Is this statement correct? Yes, it is completely correct. As you must have seen from this graph, yeah, this one, that at lower voltage your short wavelength limit is higher, but at higher voltage, your short wavelength limit value is smaller. So this question says the same thing only, that the threshold wavelength limit below which no emission occur increases with increased applied voltage. Yes. And the second statement says that the wavelength of characteristic X-ray does not change by operating voltage. Wait. This statement is also correct. The intensity will change by changing the operating voltage, not the wavelength. The third says the intensity of X-ray spectrum will increase with increasing voltage. With increasing voltage. The intensity of X-ray spectrum. This statement should also be correct, I guess. The third one. The intensity of X-ray spectrum should increase with increasing voltage. So I guess all the statements are correct in this case. Wait, wait. I have a certain doubt in this question. Let me check. There is some problem. Just a second, guys. The statement 1, the threshold wavelength below which no emission occur increases with increased applied voltage. As we are increasing the applied voltage, the limit is decreasing, no? So the statement 1 is incorrect. And the wavelength of characteristic X-ray does change by changing operating voltage. This statement is also incorrect. So I guess this question was incorrect. Yeah. sorry. The statement 1 says that the threshold wavelength limit below which no emission occur increases with increase applied voltage. No, it decreases as we are increasing the voltage. Your lambda SWS value is getting decreased. So this statement is incorrect. And the statement second says that the wavelength of characteristic X-ray does change by changing operating voltage. The wavelength won't change. There is no note, so the wavelength won't change. Your intensity will change, will increase with increasing voltage. So this statement is correct. So the incorrect statements are statement 1 and 2 both. So option B will be the correct answer for this question. The next question says that for a sample with a crystalline size of 100 angstroms and using a wavelength of 1.54 angstrom, estimate the peak breadth in radians and degrees of a peak at 60 degree as 2 theta value. So basically you have your Scherer formula which is used to calculate the size of your crystal just by the thickness of your, or we can say FWHM of your peak, which is given by beta as lambda wavelength divided by the size of your specimen into cos theta. So your 2 theta value is being given as 60 degree. So your theta will be equal to 30 degree. And your crystal size is given as 100 angstroms. And your wavelength is given by 1.54. So you just need to calculate the peak breadth in radians. Can anybody calculate it? All the values are being given. Gautam is saying option D for this question only. Anyone else? B. Selva Murugan says option B. That is 1. So basically 1.54 divided by 100 into cos theta. Cos theta will be cos 30 degree. Root 3 by 2. So the value comes around 1.02 degree. So you can write it as option B. Option B seems much closer, 1.02 degree. So the next question says, in a simple X-ray scan, which of these affects the peak position? So your peak position is affected by X-ray wavelength. Is this statement true? Yes, it is completely true. Peak position wavelength, crystal size and atomic number. Crystal size and atomic number will not affect the peak position. The unit cell parameters, that is A, B, C, alpha, beta, gamma, these will also affect the peak position. So only statement 1 and 3 are correct. This option. So option C, which says both 1 and 3 statements are correct, should be the correct answer of this question. That says that the peak positions in your X-ray scan will be affected by the wavelength of your X-rays and the unit cell parameters, but not by your crystallite size and the atomic number. These will affect your intensity and your FWHM of the peaks, not the positions. The next question says, what is the primary information obtained from an X-ray diffraction pattern? Can anybody tell me answer of this question? Since we have been discussing about the X-ray from past 1.5 hours, what is the primary information which is being obtained from the X-rays? The arrangement of atoms in the crystal lattice, the size of the crystal lattice, the composition of the crystal's color and transparency. Anyone, any guesses? People say option A. Shailendra says option C. Why option C? They are asking about the primary information. The primary information is basically the arrangement of atoms in the crystal lattice. Option A is the correct. The composition of the crystal structure you can get, but your primary information they are asking in the question, which will be your arrangement of atoms, which will be given by your peak positions and everything. So in this case, option A should be the correct answer. Is this clear to you, Shailendra? Okay. We'll go to next question. Question number 6. It says, which of the following statements is or are correct? Statement 1 says that the diffraction pattern coming from X-ray diffraction experiment is the intersection of all the causal cones in 3 dimensions. This statement is completely correct. I will just repeat this statement, which says that the diffraction pattern coming from X-ray diffraction experiment is the intersection of all of the causal cones in the 3 dimension. This is completely correct. The statement 2 says that the magnitude of reciprocal lattice vector is inversely proportional to the distance between the adjacent crystal planes. Reciprocal lattice vector, which is vector G, remember, is inversely proportional, and G was given by 1 by D, magnitude of 1 by D, 1 by magnitude of D. So the magnitude of reciprocal lattice vector G is inversely proportional to the distance between the adjacent crystal lattice plane. This statement is also very correct. The statement C3 says that the Bragg law is only satisfied by the points lying on the Ewald sphere, which we discussed in the class. So only the reciprocal lattice points which are lying on the Ewald sphere will satisfy the Bragg condition, and rest all points will not satisfy and will not undergo the Bragg diffraction. So these all statements are correct. So according to this, option D will be the correct answer. Any doubts, any questions? Are all questions clear, or is there any doubt? I guess no. Then let me go to the next slide also. It says, which of these is not involved in the diffraction of X-rays through a crystal? Anyone? Any guesses? The electron scattering, the nuclear interaction, crystallographic planes, constructive interference. Which of these is not involved in the diffraction of X-ray through a crystal? We discussed how the diffraction is happening and how the scattered radiation is going after hitting the specimen. So which of these is not involved in the diffraction of X-ray? Your electron scattering, your nuclear interaction, crystallographic planes, or constructive interference? Any guesses? Selva Murugan says option B, nuclear interaction. Anyone else? Gautam says option A, electron scattering. Can you explain me, Gautam, why you are saying option A? Electron scattering is the basic thing which is going on, no, from starting. How the electron beam are being generated, how they are interacting with your specimen, and how they are being scattered. Yes, option B is the correct answer. Please read the question properly and try to answer. So which of these is not involved in the diffraction? So nuclear interaction is not involved. So according to this, option B should be the correct answer, not option A. The question number 8 says, what is the smallest d spacing that can be measured for a given wavelength? We all know the Bragg's condition, which says that lambda is equal to 2d sine theta. And you all know, so let me rearrange it first. So d will be given by lambda by 2 sine theta. So they have asked for the smallest d spacing that can be measured for a given wavelength. So for the smallest d, this should be maximum, the denominator, and the maximum value of sine theta we all know is 1. It cannot have a value more than 1. So the smallest d spacing that can be measured for a given wavelength will be lambda by 2. So the correct answer will be option A, that is 0.5 lambda. Is this clear? Yes, Shailendra, you are very correct. It's 0.5 lambda. Because we can have the maximum value of sine theta as 1 only. So as a result, your minimum D spacing, which can be calculated using your X-ray, will be lambda by 2, which is 0.5 lambda. Any doubts? So the next question says that a crystal has a cubic unit cell of 4.2 angstrom D spacing using a wavelength. Oh, it is saying the cubic unit cell, so that means the A, B, C parameters are 4.2 angstroms using the wavelength of 1.54 angstrom. And can anybody tell me what source they are using right now? If they are using a wavelength of 1.54 angstrom, we discussed this in the theory class. If the wavelength is 1.54 angstrom, which source they are using? They are using the copper K alpha source. So crystal has a cubic unit cell of 4.2 angstrom with a wavelength of 1.54 angstrom. At what angle, 2 theta, would you expect to measure the 111 peak? So you have a unit cell parameter as 4.2 angstrom for a cubic system, and the wavelength as 1.54 angstrom, and then you need to calculate the value of 2 theta, which will satisfy the Bragg condition for 111 peak. So basically we need to calculate value of theta. For that you need to know the value of the D spacing, and you have given the wavelength, the cubic unit cell parameter, and your plane. So for cubic system, as we discussed in the previous questions only, D will be given as A divided by under root of h square plus k square plus L square. So I'll directly write h square plus k square h square plus k square plus L square का under root. So if you put the value of HKL as 111 and your A unit cell parameter as 4.2 angstrom, then you will be able to get your value of D spacing for your 111 plane. Can anybody calculate and tell me what will be the value of this D using this simple formula? Anyone? This is a very simple calculation. You just need to have the value of A and your HKL planes. Here your HKL plane is 111 plane and your value of A is 4.2 angstroms. So this will be 4.2 angstroms divided by under root of 1 square plus 1 square plus 1 square. That will be 4.2 divided by under root of 3, and Selva Morgan has already given the answer of D spacing as 4.2 as 2.42 angstroms. Yes, you are very correct. Someone, yes, Gautam, 2.42 is the correct answer for the value of D spacing. So this is 2.42 angstrom. And what we need to find out the 2D value, and for that I'll just write it here that you can use your Bragg's formula, which says that lambda is equal to 2d sine theta. Your lambda is 1.54. Sorry. You all can try with me. Your lambda is 1.54 and I can simply divide it by 2 and d spacing is 2.42, which is calculated by you people. This will give you value of sine theta So what are you getting the value of sine theta as? So this will come around 0.32. Right? Anybody else is getting this same answer? Gautam has already calculated the final answer as 37.1. Balakrishnan also says B. Okay, most of you have calculated the answer. So this theta is 18.5, but in the question they have asked you the value of 2 theta. So its double will be 37. So correct answer will not be option B, it will be option D, 37 degree. From here you can get only the value of theta, but they have asked the value of 2 theta. So the correct answer will be, correct answer for 2 theta value will be option D, 37 degrees. The last question says, what is the most common crystalline material used for X-ray diffraction studies? The most common crystalline material which is highly crystalline and have very specific d spacings and all, which is your silicon. So basically silicon is used for the X-ray diffraction studies. This silicon is very common crystalline material due to its very well defined crystal lattice, and also it has a very high availability in the single crystalline form. If it will be polycrystalline, then it won't benefit much, but this silicon is very easily available in the single crystalline form, so that's why we use this silicon crystal for the X-ray diffraction studies. Is this clear to all? Any doubts, any queries for today's class? Any question which you would have not have understood? Question number 3. Question number 3. Okay, this one. What's the doubt? peak width is basically given by the Scherer formula. There is one Scherer formula from which you can calculate the peak width, which is basically related to your specimens. Can you please mute yourself? So basically there is one Scherer formula which relates the crystal size to the peak width of your X-ray diffraction studies, which is given by the beta, which I wrote it down. I guess I have discarded that ink, which is given by this beta. There is one Scherer formula which relates your crystal size, how thick your specimens are. So which is given by beta is equal to lambda divided by your crystal size. I'm just writing it as S into your cos theta. So if your crystal size is very small, then your beta will be very high. So for nanocrystals, when you are doing your X-ray diffractions, you will get much broader peak as compared to your normal bulk sample, from where you will get very fine peak. So by looking at the peak only, you can tell that this will be your nano size regime, and this will be of high crystal size X-ray diffraction. So depending upon the FWHM only, this FWHM is the full width half maxima. This value is very high for nanomaterials and very low for bulk specimens. So this is basically given by this Scherer formula, and there is proper calculation you can do, from where you can find out what will be your crystal size depending upon the FWHM of your peaks. Is this clear to now? Shailendra, is this clear to you now? You, your voice is breaking. I am not able to hear you. Can you please type and let me know your query? Anyone else? Any doubts? Any suggestions? Any questions? Meanwhile, Shailendra is typing his question. Can anybody? Do anybody have? Okay, you got it. Okay, Shailendra, thank you. Any other doubts? Any questions related to today's class? Gautam says question number 6, option A, is it intersection or interference? Let me check question number 6. Question number 6. The diffraction pattern coming, yeah, it is intersection only, no? Causal cones, I remember we discussed in the last lecture, where we discussed about the Kikuchi lines and how the Kikuchi lines are formed from the intersection of these causal cones with your evolved spheres, which gives you the parabola. And since the angle is very small, then you can see the straight lines of the Kikuchi lines. Okay, Gautam. Any other doubts? I'll upload this presentation as well as this group meeting link on YouTube for your later reference. Is there any other doubt or any questions? Do let me know.